Good afternoon. My name is Hunter Carpenter, Senior Director of Public Policy for the Agricultural Retailers Association. Welcome to the fourth in a series of webinars ARA is hosting in coordination with CPDA, the Council of Producers and Distributors of Agrotechnology. The goal of this webinar series is to develop a uniform industry adjuvant education program for the ag retail industry so we can help growers understand how the selection and use of the proper adjuvant will improve their overall crop protection program. This webinar will give a continued look at the individual categories of adjuvants, and we continue our series with a review of what water conditioners are and what they do as tank mix adjuvants. We will explain the different types, when to use, and how to optimize performance to help the grower improve results. Today's webinar is titled Using Water Conditioners to Protect Your Chemical Investment. Today's featured speaker is Johnny Roberts, Director of Education Adjuvant Chemistry for CPDA. Johnny has 45 years of experience in the development and technical support of pesticide, fertilizer, and adjuvant formulation. 44 of those years were spent with Helena Agri Enterprises. Johnny is also the co-inventor of 15 U.S. patents related to pesticide, adjuvant, or nutritional formulations. We would also like to thank Copcoat Farm and Forest Protection for sponsoring today's webinar. We greatly appreciate their continued support. Certified crop advisors attending today's webinar can earn one CCA program IPM CEU. At the completion of the webinar, a QR code will be displayed for attendees to scan using your mobile device. Stay tuned for that. We'd also like to take this time to thank the CPDA Advisory Working Group and other contributors and acknowledge their contributions in helping plan this series of webinars. Thank you all for your hard work. I will remind everyone that Johnny plans to take questions at the end of his presentation, but you can submit questions at any time using the Q&A function provided by the Zoom webinar application. This webinar is also being recorded and will be made available on ARA's website, aradc.org. Webinar recordings and slides are made available to all ARA members and can be accessed on the member homepage. If you need help logging in, email info@aradc.org. Without further ado, I will turn it over to Johnny Roberts with CPDA for today's presentation. Johnny?
Thank you, Hunter, and welcome everybody who's joining us on our webinar today. And I'd like to show our appreciation once again for our sponsors. Very briefly, what our agenda will be for this hour we have together is, why is water quality even an important issue for pesticide application? What are the types of water conditioners we use to address those problems? How do we best use them? And then what are some of the problems that I can hopefully solve with them? And then finally, to wrap it up, why does a grower applicator even need to use them? Next slide, please. We have 5 variables with water quality that we're concerned about. There are hard water antagonisms, examples being glyphosate and glufosinate. We have issues related to active ingredient absorption. There's quite a range of materials that may have an issue there. There's the problem with high pH decomposing active ingredients such as captan and acephate. And then there's the issue of clay particles or silt deactivating certain herbicides like paraquat, diquat, and glyphosate. Next slide, please. The extension of water quality as an issue, as you can see from this map, can be quite extensive. I mean, you can range from 0 in the east and delta areas to water hardnesses that are greater than 3,000 and 4,000 parts per million when you get into Texas and some parts of the Southwest. So it's quite a variable thing that we're being asked to deal with, and water conditioners have a role in addressing it. Next slide, please. So how have we addressed water quality currently and in the past? Well, we can simply increase the pesticide rate. If we're losing activity from it at the rate that we're using, we can lower the spray application volume. We can try to make it applied as soon as possible, decrease the whole time we have it in the mixture. But the top 3 are not always options available for us. So using water conditioners is a preferred way to address these problems. Next slide, please. And today we're going to predominantly cover just herbicides. There's issues related to insecticide and fungicides, but today we're primarily concerned ourselves with herbicides. And that's because many of them are impacted by water quality. We know mineral cations, clays, all those materials together, even organic matter can be a problem. And typically with herbicides, we have a lot more references and a lot more commercial experience in dealing with water quality. Next slide, please. So first, definitions. What is actually a herbicide antagonism when we hear that phrase? And essentially what it is, chemical factors that are in the spray tank which can interfere what the normal activity of a herbicide would be. Next slide, please. So an example of herbicide antagonisms that we deal with, probably the two with the most issue and the ones that have been studied to the biggest degree are glyphosate and glufosinate. And we know that water containing high levels of calcium, magnesium, and iron can affect glyphosate's performance. And we also know that ammonium sulfate by far has been the most common water conditioning agent recommended for overcoming spray water herbicide antagonisms. Next slide, please. And there are more herbicides than glyphosate where the recommendation of AMS comes into play. We have a lot of our post-applied herbicides like clethodim, cethoxidim. We have saflufenicil, mesotriazone, imazethapyr, and several others. And the thing that we want to stress, not all of these recommendations are due to water quality issues. You'll find water quality and water conditioners being recommended in areas besides those with just issues related to pH and water hardness. Next slide, please. Again, our focus will be on glyphosate. It continues to be used on more acres than any other herbicide in the U.S. We have a lot of research data on glyphosate. We tend to know what helps it, what hurts it. The issues specifically with water quality have been extensively studied. And the principles that we learn will pretty much apply to any weak acid herbicide. So it's a great active to focus on and when you're dealing with water quality as an issue. Next slide, please. And I mentioned earlier, and I wanted to reemphasize it, how water conditioning is not the only function applied by things like AMS. And you can find references to ammonium sulfate being used to enhance herbicide efficacy all the way back to 1974. We know that some of this enhancement comes from the ammonium nitrogen converting pesticides to a more absorbable form. And we know that ammonium nitrogen can enhance spray deposit uptake. And the effects can be quite dramatic, as you can see in these images here. You can have equivalent rates of glyphosate, and the only difference being the addition of 8.5 pounds of ammonium sulfate per gallon, per 100 gallons. And you can see quite a dramatic impact on the weed control. Next slide, please. But when we deal with water hardness, we'll start with that part of it first. And we basically define hard water as water containing metal cations. The three that we are most interested in when it comes to antagonizing glyphosate are iron, magnesium, and calcium. We collectively call them hard water. There are other cations that are obviously out there and available, but these are the primary three of concern. And we like to say that the water can be soft, and we typically find that as 0 to 50, and water can be hard, which we typically define as 100 and up. And in terms of the impact that this can have on glyphosate, we know from research and long years of commercial experience that there's really no impact on glyphosate from the hard water standpoint when you're less than 60 parts per million. When you get to 60 and 180 parts per million, there's a moderate to strong impact, and greater than 180, there can be a potential for severe impact. Next slide, please. So to better understand what's going on chemically, Glyphosate is an anion, and depending on the pH, you can have as many as 3 negative charges. And it's these negative charges that interact with other things that are in the spray solution. When we utilize glyphosate, it's in the form of a salt, and typically it's an isopropylamine salt, as you see here, or in the case of other materials, it can be a potassium salt. So what happens when we introduce a positively charged metal cation from a hard water issue to a mixture of glyphosate and water? Advance, please. And the one we're interested in is calcium. And as we know, calcium has a +2, and it can readily interact with the negative charges on the glyphosate. Advance slide, please. And when it does, we create essentially a new compound, a new form, a new salt. And in particular, it's a calcium glyphosate salt that has very low water solubility. And what does all this mean? Advanced slide, please. If we look at spray droplets of a glyphosate solution applied in soft water and one applied in hard water, and we look at it as an electron micrograph, and in this case on Johnson grass, you'll notice in the soft water that the coverage is uniform and complete. There's obviously everything in solution. There's nothing that's on the outside, but contrast that in the hard water, and you could see a granular formation, a layering. These are materials of glyphosate combined with the hard water cations. And what the impact of that is very, very slow absorption, uptake, or none at all. So it can be quite dramatic depending on the level of hardness. And this is a real good visual indicator of what turns into the final conclusion of lack of control. Next slide, please. So how does lowering the spray application volume enhance glyphosate activity? And we know from the water quality issue, it's just simple math. I mean, if you start with a higher volume of spray application liquid per acre, and we drop that spray application volume down, we have less of the hard water cations to cause an issue. For example, if you're applying the same dose of glyphosate in 5 gallons of water that you're applying in 20, you would have 4 times as more hard water cations compared to 5. So that's an obvious way, and one that we have been using for many years to mitigate the problem. But in addition to cutting back or diluting the number of hard water cations, there's also another positive in reducing the spray application volume. Next slide, please. Kramer and Linscott back in 1990 and 91 published a paper where they showed how spray deposit characteristics can have a dramatic impact on performance of glyphosate. Advance, please. And another advance. And what they found was that you could have that glyphosate dose in one large droplet and actually get more activity than you would if all that dosage was applied in multiple droplets of the same size. Next advance, please. So essentially, glyphosate is more phytotoxic when applied in a concentrated drop than in 9 dilute drops of equal size, meaning that the more concentrated that mixture is in a given droplet of water, the more likely you're going to have a positive phytotoxic effect. Next slide, please. Now, why published some published some work back in 1995 where they theorized that this was due to something they called the pile deposit effect, which essentially confirmed what was noted earlier, that if you had all this glyphosate concentrated in a smaller volume of water, the uptake was greater. And adjuvants that allowed that to happen would in turn enhance the performance. So they theorized that this is one of the things that ammonium sulfate was doing. It was one of the things that urine nitrogen was doing. It was something that any number of adjuvants would do. And really, if you consider what is happening from a physiological standpoint, your diffusion is better when all of your active ingredient is concentrated in a smaller droplet of it can be even a larger droplet of water. The rate of absorption, the degree is greater and by diffusion when that occurs. Next slide, please. So I mentioned earlier how AMS was the original herbicide water conditioner. It began to appear as a recommendation on Roundup labels back in the late 80s. NDSU and Michigan State did a lot of work very early, proving its value and determining the mode of action, which has been invaluable to understanding what water conditioners do. And we now know that it's essential to good performance of several herbicides. And one of the things that's come out of this long work with ammonium sulfate is the introduction of alternatives to ammonium sulfate. Many of these alternatives are liquids, easier to mix, easier to use, and a lot of them have been introduced and have some advantages over AMS alone. But still today, AMS is by far the most common. Next slide, please. The way AMS works from a water quality standpoint is that when we introduce sulfate ions, like we show here in this picture, we have two negative charges that readily compete with the glyphosate for the magnesium and calcium positive charges that are present in hard water. And by doing so, it essentially keeps them from binding with the glyphosate or retards it and prevents the antagonism. Next slide, please. There are alternatives to AMS, and we will be discussing those. We can do things like modify the alkalinity and acidity with pH modifiers and buffers. We can chelate hard water cations with EDTA, citric, or glucoheptanate. We can use something called AMADS, which is also been called an acidic AMS replacement. And there are even large molecular weight anionic polymers that have been used as water conditioners in pesticide applications. Next slide, please. In the case of AMADS and what this material is and how it come into the marketplace, it's essentially a reaction product between urea and sulfuric acid. Sulfuric acid has been used for many years in the western part of the U.S. to address line issues, irrigation line issues being clogged with calcium deposits, and it's quite problematic to deal with. This has a lot of worker hazard issues, corrosion issues, and by mixing it with urea, it was found that you could essentially make it a much easier, safer material to deal with. And for a long time, this use was limited to just water conditioning for irrigation line cleaners, but they found through testing and research that it also has a pretty good absorption enhancement of some pesticides, particularly glyphosate. There was a series of patents published in the late 80s, and this turned into commercial products. And these materials collectively have been called AMADS. Next slide, please. And what AMADs do, they've been demonstrated to have a greater absorption enhancement potential than AMS. And the use rates for that reason are typically lower than AMS. And they've also been used not only in adjuvants, but also as an in-can co-formulant with glyphosate and ethifon, though these materials are no longer on the marketplace. But this is a case where there was an attempt to basically build the adjuvant function in, and they were successful with these two active ingredients. And then you'll find other products in the marketplace today that are co-formulated with surfactants and deposition agents to provide other benefits and functions for the grower and applicator. Next slide, please. Some other alternatives to AMS or complements to AMS that have been used are chelators. And there are two predominant ones that we use, EDTA, and the other one being citric acid. And what these materials to do, the ammonium sulfate, they use an anionic charge to interact with the hard water cations, but they produce a complex, a structure that is much tighter than what would be as opposed to just the sulfate alone. So these materials are quite effective in addressing hard water issues, though as of yet today, they have not been demonstrated to provide any absorption enhancement capabilities. But in the standpoint of tying up metal cations, they're very effective. Next slide, please. Another group are the anionic polymers. These materials are used extensively as water conditioners today, but in other industries, they are used to keep boiler lines clean. They're used to keep irrigation lines clean, plumbing clean. They're essentially large polymeric polymers with many, many negative charges that are capable of binding to hard water ions and keeping them from interacting or falling out of solution. They too work at lower use rates than many of the other water conditioners, but alone they are not likely to enhance any pesticide uptake or absorption. Next slide, please. So some application notes, and it's important and to understand and deal with some of the guidelines that apply to using water conditioners, and we'll be emphasizing it from this point forward. But one thing to keep in mind is that simply acidifying a spray mixture does not correct all water quality problems, and it may actually cause other issues. And the bottom line on this is that there are some pesticides that just do not need to be acidified, and we'll be discussing those. And then another good rule of thumb is that all water conditioners should be added to the spray water first, and then they should be fully mixed before adding other components. And as you could imagine, logically, you want to prevent a problem, and best to condition the water before you add the pesticide. And also from a mixing standpoint, things go much, much better when the water conditioners are fully diluted in water first. Another very important rule of thumb is that we never mix pesticide products directly with undiluted water conditioners, be they of any type. This practice can cause a lot of mixing issues and application issues. So we never want to pour pesticide products directly into undiluted water conditioners. And then the other point we want to stress is that water conditioners may be needed even when the water quality is good. And this is an area that we want to discuss and explain why this is indeed the case. Next slide, please. Lamb's quarter and velvet leaf are two weeds that are notoriously problematic with glyphosate. And as we all know from experience in dealing with them, glyphosate can be either ineffectual or take very, very high levels to control them. And this particular weed has recommendations for levels of ammonium sulfate that typically are much higher than or for other uses. And you'll find these recommendations are being made regardless of water hardness. And a lot of them even have so far as to include not only with the ammonium sulfate, various highly penetrating or absorption enhancing type adjuvants like COCs and MSOs because of the problems associated with these weeds. And what these problems are due to is that these two weeds are examples of plants that are able to actually produce calcium that is secreted onto the outside of the leaf surfaces. So it doesn't matter your water hardness, how quality of your water, you're dealing with calcium that's actually on the outside of the leaf surfaces, and that calcium in turn deactivates the glyphosate that is being used to hopefully control this. Next slide, please. This is some work that was done to show the impact of this. And what is interesting is comparing 1,700 part per million water to 12 part per million water, a very, very, very soft water to one that's very, very hard. It's comparing the two. and then showing the impact of using water conditioners. And what's interesting here that in this particular case with lamb's quarter, even the soft water was showing a dramatic improvement in activity from 56% control to 86% when ammonium sulfate-based water conditioners were used. There was almost the equivalent effect with the hard water. And because from this standpoint, it just didn't matter what the spray water water hardness was, because you're dealing with a leaf tissue that had so much more calcium in it to begin with. So that's an important note. Be aware of that when you deal with water conditioners, that water hardness is not your only indicator that a particular water conditioner would be needed. Next slide, please. So another issue that has generated problems over the years, and it's still problematic today, is this issue of buffers versus acidifiers. And acidifiers essentially are materials that reduce spray mix pH, but they may not necessarily maintain it. And in some cases, they may go down to numbers that are just very, very, very acidic. And even from a worse standpoint, even though they take the pH down, they don't necessarily hold it. Examples are phosphoric, sulfuric, muriatic, citric, vinegar. And as compared to a buffer, what these materials will do, they'll modify pH to a certain value and maintain it. And something that is often missed is that there are both acidic buffers and there are alkaline buffers. And so a buffer can be either one. So depending on the type of pH you're looking for, buffers can be either low pH or high. An example of a buffer product that is in the marketplace is a phosphate ester surfactant. These materials have been used extensively through the years to address water quality issues, to address pH issues. And these materials are, when they're formulated correctly, are true buffers. They go to a particular pH and they tend to hold it there. But the real thing I'd like to discuss and stress is how not all sprays require lower pH, and in fact may be negatively impacted by it, because there's oftentimes an incorrect assumption that if I just lower the pH of a given spray mix, then I've solved all my water quality issues and uptake issues and so on. Next slide, please. So what do labels say about this particular issue? And some of you may have been curious about on the Roundup PowerMax labels that there is a direct prohibition against adding any kind of a buffering agent or pH adjusting agent to the solution. And when particularly when it's the only herbicide that's being applied, and it's always been a curious restriction a lot of people weren't aware of, but we'll explain what's driving it shortly. On a label of Coside 2000, there's a warning that if you apply the material at a pH less than 6.5, you may actually get phytotoxicity. And then you have the other extreme. Here we have 7-SL, which is a carbaryl-based insecticide, and you're having a warning here on that label not to use anything with a value greater than a pH of 8. Next slide, please. So this issue is a lot more complex and doesn't lend itself to simply dropping the pH. Go back to the glyphosate prohibition that the Roundup label has. When you get the pH below 3, you run the risk of the glyphosate falling out of solution. There's a solubility loss. That is why the prohibition that is on that label is a concern that you may get the pH so low that the glyphosate falls out of solution. This is one of the reasons why we stress that you do not mix undiluted herbicide products directly with water conditioners. That's the worst case scenario of the solubility loss. Then you have on the other extreme, if we have a really alkaline pH getting above 7, then active ingredients like captan and carbamate can actually decompose. When we have a pH less than 6, we can have a solubility loss between dicamba, famosophin, triclopyr. These materials can actually fall out of solution when the pH is below 6. This is a problem that is really not been that much of an issue until the last, I'd say, past 10 years. And what is driving it is that now that we are getting lower application volumes per acre, there's less water in them for dilution of these herbicides if they do fall out of solution. So again, another example of why we don't always just carte blanche drop the pH of materials and assume that it's going to improve. Another issue to be aware of is with sulfonylurea herbicides. And as we all know, these materials have a very important clean out issue. When you have the pH on the acidic side, they tend to lose solubility in water and are much more difficult to remove. So that particular case, if you have a lower pH with sulfonylurea herbicide, all that much more and more important to use tank cleaners that have a higher pH to raise the pH value above 8 to make them more soluble in water. So hopefully you can see how complex it can be. We need to know what we're doing when we're modifying spray mix pH. Next slide, please. So what's the bottom line? Well, obviously we're going to start with clean spray water and use the adequate rate of the herbicide. Pushing those rates lower makes them that much more susceptible to water quality issues. And be aware that we have no magical components out there, adjuvants to remove clay and silt and organic matter that could be causing a problem. You know, those are things we just have to avoid or highly filter the water. So start with clean water to begin with. Use as low a rate of application as is practical and permitted by the label. Typical ammonium sulfate recommendations that will work in most cases of water are 0.5% weight per volume, but realize you know, that can go up depending on how high the water hardness is in a given area or a particular weed you're trying to control. And then the AMS replacements, you know, a lot of these materials offer some real advantages over AMS, but use them at the manufacturer's recommendations. Don't fudge on the labels or use things assuming that based on past experience that this alternative product would work the same way. Never assume that all spray mixes require acidification. And if your glyphosate rates are on the low side and your spray volumes are high, it's always wise to include a non-ionic surfactant. And as we know from our experience, the more stressed weeds are, the more difficult they are to control and manage. Next slide, please. So what are some of the problems that you may run into that a water conditioner product might address? And we've talked in great length about the antagonisms, but there are also situations where mixing and compatibility issues that may have nothing to do with efficacy can come into play when water hardness or water quality is an issue. So consider some of these materials for their compatibility needs, their abilities to keep, for example, hard water from interacting with soaps and various other things and moving them out of solution. We can utilize many water conditioners to prevent active ingredient decomposition, which is an issue we have to manage. We know that we can increase the degree and rate of absorption, which is always a positive, in particular when we're trying to offset rain fastness and things of that nature. And then keep in mind the specificity issue against certain weeds. And again, the herbicide manufacturer is often your best guideline there, but realize there are some situations, regardless of water quality, where a application could be enhanced by using a water conditioning agent. Next slide, please. So what does it all mean? Well, as always, we refer to the label first. You'll find that there is a lot of well-established recommendations for AMS. In particular, there tends to be a range on the recommendation. Depending on that water hardness, you can use a higher or lower rate. Some of these are suggestions, others are requirements. And then what are the other adjuvants that you're including? Realize that water conditioners do not take the place of surfactants and oils when they are recommended. You'll find some products where they're actually able to combine surfactants and even oils to put them in one container, but realize it's the same guidelines. If it's a contact herbicide like glyphosate, typically it responds to surfactants. If it's systemic, it typically responds to oils and silicones. And then what are the problems that you're trying to solve? If it's pH, what is that water conditioner that I'm considering able to do for me there? Does it take it down to the level I need? Does it do it too much? Does it do too little? Am I trying to manage hard water, or am I simply trying to enhance absorption? Next slide, please. So inevitably, you'll have customer questions, concerns about using water conditioners. We're going to talk about the objections and what those rebuttals would be. The one about manufacturers would build them in if they were actually needed. Realize that it's very difficult to do a one size fits all for any of these type of materials. One of the things that we do not want to see in the U.S. is geographic specific pesticide labels. And adjuvants allow us to address these many variables that are out there and allowing us to use essentially a 50-state label. And it is not always possible or even advisable to build a water conditioner component into these materials. So it's just something that has not been done. Acidifying the spray mix is enough. And if we've discussed that not all pesticides should be acidified. In fact, you may increase crop injury and compatibility problems when you do that. There is a perception that a lot of water conditioners cause foam problems. Some of them are quite foamy, but not all of them are, and many of them have been formulated as a way to manage that. And for those that do, what you'll find is that in the majority of the cases, the foam problems are easily controlled with foam control agents. And in terms of, this is just one more input I have to add that increases my costs. But as we've always pointed out, prevention of application and efficacy problems is likely a cheaper alternative than having to respray or use a higher rate of pesticide. Next slide, please. And with that, I think we'll be about ready to take some questions.
All right. Well, thank you, Johnny. And I know we have a couple of questions already in the chat, so I'll read those out to you and let you answer them. The first one is, what was the rate of RU WeatherMax used in the water conditioner test in very hard and very soft water? What is the composition of the water conditioner that was used at 1.25% and 2.5%?
Okay, the glyphosate rate was a very low rate, almost, as I recall from that particular work, below label rate. And this is often done to pull out differences. If you're doing adjuvant studies in particular with the middle and higher rates, it's difficult to discern differences. In terms of the compositions of the water conditioners, that particular study is unknown to us. Most of these compositions, if not all of them, are proprietary at some degree or level. So I'm not able to don't know particularly what that one was. I do know it was AMS based.
Next question. If a customer installed a water softener to fill his sprayer, he thought it would improve his water and reduce hardness. After testing his water, it did not reduce bicarbonates. How does softened water impact spray?
Yeah, those materials are designed to take out the hard water cations, the calcium, magnesium. They'll do iron, they'll do fine for that. They may not address, and most of them don't, the carbonates and bicarbonates, which are a different issue altogether. Water conditioners tend to remove them because they're acidic, but with the those type of column or cartridge conditioners, they were really not, most of them anyway, designed to do that. Also, keep in mind that those filtering materials do not aid in enhancement. of uptake and absorption the way many of these materials are meant to do.
Next question, since the silicone super spreaders have shorter lifetimes outside of pH 7, have systems been buffered solely to prolong their utility, or is the amount of longevity gained not helpful?
Yeah, there has been work in that area. I know there are certain organosilicones that are much more stable in acidic pHs. For the studies I've seen on it, as long as that spray mix is applied pretty rapidly, unless you've got an extremely acidic material, I have not seen detrimental impact on the organosilicone. It probably would show up if you kept it for more than 2 days, at least one that is not hydrolytically stable. But just on the normal spray and use, we have not seen or at least I have not seen a negative impact from having the pH less than 7.
Next question, I've seen claims that ammonium ions cause herbicide ion trapping by creating a pH grade between the inside and outside of the plant leaf surface, allowing more herbicide to be absorbed. Is this true, and can you expand upon it?
Ooh, I'm not familiar with that particular theory. I've heard of the situation where the excess ammonium ions that are on the outside of the leaf that come from the application of them results in a proton moving out from the plant tissue. The hydrogen pump is what that's been referred to. And this movement out of hydrogen to balance the ammonium that's on the outside results in a pumping action, so to speak. But I'm not familiar with the other concept that was mentioned there. That's a new one to me.
Next question, how do you decide the dose rate of the anionic polymer?
Oh, that you can theoretically, you could calculate them. They have a long legacy in water hardness use, reduction in use. You can calculate what the theoretical reduction is, but at the end of the day, it's hard to replace replicated field application trials to determine what that data is. You have the variables in particular, and it's a big variable. Once you get outside that spray mixture and you're onto the leaf surface, and as I understand it, the majority of these broadleaf weeds tend to be alkaline on their outer surfaces and have some degrees of calcium and things like that. And you will miss that with your theoretical calculations of what you're doing with these polymers in hard water. So to answer the question, yes, you can calculate it, but in the day, you need replicated field trials to demonstrate what that effective use rate would be.
Next question, why hasn't other ammonium salts been used, for example, ammonium EDTA?
That's a good question. And actually, that issue has been studied quite extensively. And yes, you can get positive impacts from other ammonium salts. I think the reason we have pretty much settled on ammonium sulfate as an industry is that it's widespread availability. It's a fertilizer that is available to a wide range of people, and so it's just become from a logistical reason the go-to source. Now there are others that have been studied. I know ammonium bisulfate has been looked at for this. You mentioned ammonium EDTA. That's an interesting one. But ammonium sulfate has become the most cost-effective solution for this when your goal is to get ammonium nitrogen.
Next question, do many of these water conditioners promote foam? Sometimes I like hard water for helping with the foam, but now I can see this can be detrimental.
Yeah, so well, some of them by themselves are foamy, and we have seen situations where the water conditioner makes the foam worse or it makes it better. There's such a variability in formulation types. You'll find that many manufacturers have found ways to incorporate foam control agents directly into their water conditioner products. And so I guess the answer would be yes, some cause foam, but some actually reduce it.
Next question, it's commonly said that liquid water conditioners cannot do as good a job as AMS. Is this really true?
That can be true, yes. But understand there's two modes of action that we're doing here. You know, when the mode of action is to tie up calcium and magnesium cations, you know, we can oftentimes equal or exceed the performance of ammonium sulfate. However, there is that enhancement piece that, you know, due to the ammonium nitrogen, that a lot of these materials are not able to replace. And so the only way that you can make up that difference is that either you're formulating these materials directly into an ammonium sulfate product, or you're using surfactants and other components to make up for that either lower use of ammonium nitrogen or absence of it. So the answer to that question is, yeah, 101, many of these materials that are, and particularly the ones that are just water conditioners only, will not equal what ammonium sulfate does. But you can formulate other performance attributes into these materials and equal the performance, or in some cases exceed it, like you can with AMADs.
Next question, if a tank is mixed, but it rains or application is delayed for overnight or over a few days, how would using a water conditioner affect the efficacy results?
Ooh, that's a good question. Some of them, you know, I think some of these antagonisms are reversible. You know, so if we have the material that, you know, say like we've buffered it or we've sequestered it in a way, we're able to head off the passage of time. But you know, it's still, and I know reality, you know, if you're going to get rained out, equipment breaks down, it's still best to apply as soon as we possibly can. But I think in many cases, depending on the application and the pesticide and the water conditioner you're using, you can get some longevity to that spray mix, particularly if if it's a active ingredient like an insecticide that is subject to decomposition by alkaline pH. Then a buffer is able to hold that and maintain it over a period of time, and you would not have that as an issue.
Next question, any advice on how to understand water conditioner products that do not disclose active ingredients? For example, on the label, proprietary blend of spray solution acidifiers, non-ionic and amphoteric surfactants, inorganic hydroxides, etc.
You know, unfortunately, no. There's because the adjuvants and water conditioners are part of adjuvants, are not pesticides. That people do not have to disclose and detail their individual components. And there are a lot of proprietary compositions that are in the marketplace, and very, very few of them, if any, have patent protection. So trade secrets are really the only thing that manufacturer has in terms of protecting their intellectual property. So there is a tendency not to want to disclose in every detail the amount and the type of material that is being used. And so you're essentially at the you know, mercy of the supplier. That you know, it's always wise. Well, what is your data supporting this particular use? What is your history of supporting this particular use? But for now, the labels will be not all that revealing in terms of the components that are there.
Well, thanks, Johnny. Oh, wait, we have one more question. When do you foresee that the adjuvant industry is regulated and forced to disclose ingredients?
Well, that's already happened to some degree in California and Washington. In those two states, you do have to disclose. I know in the case of Washington, and supposedly California is following it, your three primary components have to be disclosed in the label. and you have to use nomenclature that is on essentially what a list that they recognize. But outside of those two states, it's a very, very slow process. When is that going to happen? We forget sometimes we're 50 individual countries and we're moving at different areas. I would say unless you had some kind of national, federal regulation requiring such disclosure, it's going to be a very, very slow process. Oftentimes, you can get information about components based on the SDS sheets, but typically that's only when the ingredient is contributing some kind of hazard to it. So to answer your question, I think it's going to be very, very slow unless there is some federal intervention before this happens.
Next question: in water testing, we see a difference in bicarbonate response to sulfuric, phosphoric, and citric acids. The pH may be affected, but the bicarbonates are not. What are your thoughts?
Well, once you get the pH below 6, you should make the bicarbonates dissipate. They have some resilience, compared to carbonate, but once the pH is below 6, they should dissipate.
Well, look, thanks again to Johnny Roberts with CPDA for coordinating this webinar with the Agricultural Retailers Association. On your screen, you can see the date and time for the next webinar, using drift deposition aids to protect your chemical investment, April 13th at 1 p.m. Eastern. Also, CCA CEU credit available for that webinar as well. We want to once again thank Copcoat Farm and Forest Protection for their sponsoring of this webinar. I've got Johnny's contact info there on the screen if you'd like to contact him for more info. And finally, the slide for the CEU credit, feel free to scan this QR code. I'm going to leave this up for a few minutes. And we want to thank everyone for attending today's webinar. If you need help accessing this webinar, please email info@aradc.org or go to ARA's member homepage to access the recording. I want to thank Johnny again for being on today. I want to thank CPDA and their staff for putting together a great resource for our members and for the ag retail industry. So once again, Johnny, thank you. Thanks to your team.
And thank you. Thanks for everyone attending.